Hello, Vlad. I've got a little bit of a problem today in that my daughter is at home and my wife is stuck in traffic. So if we get a 5-year-old coming in asking for snacks or a glass of water or stuff like that, that might happen. So apologies about that. You might need to step in and rescue at various bits.
Okay.
Shall I get started?
Yeah. Yeah, absolutely.
Okay, so I'm just going to share my screen. And like last week, I think it's really, so I believe that you've had a session looking at kind of rational inequalities, so inequalities with sort of linear functions, fractions, stuff like that. We're going to look at slightly more complicated inequalities today involving powers, roots, moduluses, logarithms, complicated logarithms, trigonometric functions, exponential functions. So fun stuff. Right, what I thought I would start with is a math multiple choice question. Okay, and I will give people a couple of minutes, 5 minutes max. Okay, I'll sort of judge it by the chat to have a look at this math multiple choice question. So it says let A, B, and C be positive numbers. There are finitely many positive whole numbers x, y, which satisfy the inequality AX is bigger than CBY. And it says this is true if, and then it gives us 4 conditions. So what I'd like you to do simply is once you think you've deciphered what this question means, and then once you think you've got an answer, to put your letter into the chat. People are still thinking. If it doesn't disturb you too much, can people put into the chat what they're currently doing? Okay, I won't put it into the chat, but I will say what I would do in your situation, and I would sketch to try and get the general shape in each of the four scenarios. Very quiet. Okay. If you're thinking, don't let me mess with your chi, but I'm just aware that we've got limited time and this is being recorded. So I'm going to start doing sketches for A, B, C, and D. Okay. So for A is greater than 1. So A to the X, now remember we're only looking at positive whole numbers, but A to the X in part A is greater than 1, so it's an exponential function and it's increasing. Okay, and when x is 0, it will hit the y-axis at 1. And then at the integers, it will be a, and then a squared, and so on. Now, b to the x, if b is less than 1, will be a decreasing exponential function. Imagine if b is equal to a half. We go half, then a quarter, then an eighth, and so forth. Now, it will start at c. Okay, but what we can see here is that for lots and lots of whole numbers, for whole number pairs, ax is going to be above by. Yeah, because, for example, the way I've drawn it here, a cubed is going to be bigger than, let's say it's bigger than b4. It's also going to be bigger than b5, then b6, then b7, then b8, and so on. So in part A, the a to the x function is very often going to be above the b to the y function. Okay, every pair of integers, every x and y pair, where the x is on the ax curve and the y is on the by curve and the ax is above the by, is going to be a pair. So A is definitely not the right answer. What about part B? Well, they're both decreasing. But what we can see here, if in particular, if the B curve is decreasing, now even if it starts at a high level, at some point it's going to be beneath a to the 1. And once it's beneath a to the 1, so once this CBY curve is beneath a to the 1, it will always stay beneath a to the 1. So the pair where x equals 1 and then y is any one of these numbers will be an instance when a to the x is bigger than c times b to the y. So there will be infinitely many. And in fact, I've also covered part C, okay, because I've already done the case when they're both less than 1. So this picture covers B and C. So the only one which is left is a is less than 1. So a to the x, y equals a to the x is going to be some decreasing function. B is bigger than 1. And even if it starts low, y equals b to the y eventually is going to overtake a to the x. And what we can see is that the only whole numbers when a to the x is bigger than b to the y is when an x is one of these guys and when a y is one of these guys. Okay, and then there's obviously a finite number of whole number x, a finite number of whole number y, so there'll only be a finite number of pairs. Okay, so in picture D, the a to the x function is decreasing, so is eventually small. The b to the y function is increasing, so is eventually big. So for large x and large y, or large enough x and large enough y, the ax function, the y equals a to the x function, will be beneath the y equals b to the y function. Now, people were very quiet in the chat, so I can't even say well done if you put it into the chat. But the correct answer for this one is part D. And what is the kind of moral of that question? The moral of that question is sketching is a crucial skill and, you know, almost always the best first way to attempt these problems. Okay, does anyone have any questions about that math problem? Just to reassure me that people are alive well here, can you just put a thumbs up if you liked and understood that problem? Lots of thumbs up. Good. So people are here. That's nice. Okay. Notice, and I think for those of you who are thinking of courses that are applying, you know, who want to apply for math courses, notice that this, compared to what we're going to do in some of the later problems, is what I would call very conceptual. And I think that's one of the reasons why this is quite a hard problem, because it's I think in school level maths, we do a lot of computations where we do a lot of algebraic processing. Here, because A, B, and C aren't whole, real numbers, it's a lot more just about sketching and trying to get the right picture in mind. See, warm-up, that was the warm-up question. Right. Question number 2, and inequalities with square roots. So it says, solve the inequality for real values of x with this square root. So root x plus 2 minus root x minus 1 is greater than root 2x minus 3. What would be people's instincts to do first? We've got lots of square roots. Now, we don't particularly like these square roots. They're quite ugly. So what mathematical operation might we want to do to get rid of the square roots? Square all of it. Excellent. Okay, so now we know for a fact that if we've got an equation, so if A is equal to B, we can definitely say that A squared is equal to B squared. Okay, but is the same thing true for an inequality? So is this statement true? If A is bigger than B and A and B are real, then A squared is bigger than B squared. Now, what I'd like you to do is vote in the chat and tell me if you think this statement is true or whether you think this statement is false. False, good. Right, why are lots of people saying false? Can anyone give me a counter example? Or can anyone tell me what I would need to say to make it true? Consider negatives. Excellent. I think you'll all agree that -1 is bigger than -2, but if I square both sides, 1 is bigger than 4 is definitely false. So when would this statement, A is bigger than B, imply A squared is bigger than B squared? Now, if I take away that problem of negative numbers, if both sides are positive, yeah, if 3 is bigger than 2 and 9 is bigger than 4, okay? So here, if I change this, instead of saying A and B are in R, if I say that A and B are positive numbers, then this condition becomes true. So what I need to ask myself is, to the person who said I've got to square it all, okay, are the two sides of this inequality positive, or could they be negative? Now, if they were negative, I would need to think a little bit carefully. So again, put it into the chat. Is square root of x plus 2 take away square root of x minus 1 always positive? And is the square root of 2x minus 3 always positive? Vote in the chat. So are both of these terms, this term, the green one, and this term, the yellow one, always positive? If you think they are, say yes. If you think one of them is, one of them isn't, say the green one is, the yellow one isn't, or whatever. Both always positive, okay? Excellent, okay? And this green one is positive because x plus 2 is bigger than x minus 1. Okay, now what I want to do is, because of where you're at, I want to work a little bit on what you would write when you're writing things nicely. So what I've written so far, this is just like scratchy. But if I was doing this question for real, I would say, because square root of x plus 2 take away square root of x minus 1 is, and square root of 2x minus 3 are both always positive, I can square both sides. And if any of you were going to take an exam like STEP at the end of next year, this is what the STEP examiners would be looking for. I'm not saying you need to write loads, but you need to write enough to show the examiner that you've considered the problem of negative numbers. Right, so let's square both sides. So the original inequality implies, so the square root of x plus 2 take away the square root of x minus 1 is bigger than the square root of 2x minus 3. That implies, because I can square both sides, I just square things. So I've got x plus 2, because that's square root of x plus 2 all squared. Take away 2, and then I can square. If I multiply square roots, that's the same as the square root of the product. So I get x squared plus x take away 2. And then I square the square root of x minus 1. So I pick up an x minus 1. So I've squared the left-hand side. And then what happens when I square the right-hand side? That's quite amusing, that when I square a square root, the square root just goes away. So I get 2x minus 3. Okay. And I can neaten this all up. I get x plus x cancels with the 2x. Plus 2 take away 1 is 1. I can add the 3 to both sides, so I get 4. And so this inequality is equivalent. In fact, the first one is an equivalence as well, to 4 is greater than x squared plus x minus 2. And so now that's equivalent to the square root of x squared plus x minus 2 is less than 2. Okay, any suggestions for how I can tackle what you would be inclined to do, next? So suggestions in the chat for, we've reduced the initial inequality to something which looks a little bit simpler. So suggestions in the chat for what you would do next. Okay, so square both sides and work out the quadratic. Okay, that's a good suggestion. What do we need to be a little bit careful about? In terms of squaring both sides. So we're saying the left-hand side is less than 2, the left-hand side is greater than negative. Well, no, the left-hand side, the inequality just says the left-hand side is less than 2. Now, the issue with squaring both sides is we need to again ask ourselves if things are positive. Now, because all the terms are positive, okay, that's what I was looking for. Yeah, we can square both sides because this square root by definition is a positive term. So again, let's write it so the examiner can see. So because square root of x plus 2 minus 2 is positive, we can square both sides. So we get x squared plus x minus 2 is less than 4. And again, it's an implied and implied by. And now we get x squared plus x minus 6 is less than 0. And we know how to deal with quadratic inequalities. We factorize, and we get roots at 2 and -3. And because it's a positive quadratic, we're between the roots. So we get -3 is less than x is less than 2. Is this the final answer? Yeah, check under the original square roots, okay? Because this squaring of both sides, the square root of x squared plus x minus 2 is only going to be x squared plus x minus 2 if x squared plus x minus 2 is positive. If x squared plus x minus 2 is negative, okay, then the whole thing doesn't work. So at this stage, we would also need x squared plus x minus 2 to be bigger than 0. And we know how to deal with the quadratic inequality. So we've got x plus 2, x minus 1 is bigger than 0. This has got roots at 1 and -2. And so this implies that that x is less than -2, or x is bigger than 1. And now for both inequalities to hold, we need x to be bigger than 1, but less than 2. Right, let's take a vote here. Is this the final answer? Put a thumbs up if you think that this is the final answer. 1 is less than x is less than 2. So to recapitulate, I've checked that this square root, x squared plus x minus 2, is in the right range, that it's between 0 and 4. But is there anything I've not considered? Well, let's look back at these original square roots. For this square root to make sense, x plus 2 needs to be positive. So x needs to be bigger than -2. For this square root to make sense, x needs to be bigger than 1. But for this square root to make sense, x needs to be bigger than 3/2. So what we need to say at the outset is that, but note, the original square roots only make sense for x bigger than 3/2. Okay, so what we've shown here is that if the square roots are well defined, the inequality would hold between 1 and 2, but the square roots are only defined when x is bigger than 3/2. So the overall answer, so the final answer, is 3/2 is less than x is less than 2. Okay, so what's the main What's the main moral of this? What's the moral of this question? What have we learned through looking at this question involving square roots? Why wouldn't it be non-strict? Yeah, well, yeah, clever. Yeah, sorry. It only makes sense for x greater than or equal to 3/2. So we just need the square roots to be defined. So this is a non-strict inequality. Well done, Adam. Okay, but what's the main take-home message of this question in inequalities involving square roots? There was a certain amount of algebraic processing here. But what was the hardest part of the question? What expended the most amount of brain work? Okay, I think without doubt the hardest bit was being careful about signs. Yeah, excellent. So Ira said checking whether it's positive, or negative, checking the original conditions and stuff like that. And I think this is the reason why inequalities are harder than equations. In equations, you can afford to be a little bit sloppy and just always do the same operation to both sides of an equation. With an inequality, you have to be a little bit more careful about whether you can square both sides or things like that. Okay, any questions about that question involving roots? If people are happy for me to continue, put a big thumbs up and we'll move on to a modulus inequality. Good, lots of thumbs up. Excellent. Okay, let's have a look at this modulus inequality. I'm just going to buy myself a little bit more space. That's going to ruin the PDF afterwards. I'll have to neaten this up. Okay. Okay, so it says, solve the modulus of x squared plus 4x plus 4, take away 2 times the modulus of x plus 2 plus 1 is less than a half. Okay, any thoughts, comments, observations about this example? Now, what I'm going to do is I'm going to save people a lot of pain here, okay? Because there's an alternative universe where I could picture diving in, starting to do lots and lots and lots and lots of algebra, maybe squaring both sides, getting into something really, really complicated. But Adam Thomas, has put this into the chat, that he's noticed something interesting about x squared plus 4x plus 4. Okay, and the sort of moral here is that sometimes with questions you should just take a little pause before you dive in too deeply. Okay, so before we do any algebra, let's just notice that x squared plus 4x plus 4 is x plus 2 squared. Okay, now question, and I'll put this into the chat. Okay, is x plus 2 brackets squared modulus always the same as x plus 2 modulus squared? So we've got a vote for yes. Got another vote for yes. Excellent. Okay, because if you take a negative number and you modulus it and then square, so 2 squared, that is the modulus 2 squared is 4. But what's also equal to 4 is negative 2 all squared. Okay, and if you take a positive number, you modulus and you square it, that's also equal to the number squared. So in general, any number modulus squared is just equal to the square of that number. So x plus 2 modulus squared is the same as x plus 2 squared. But x plus 2 squared is positive, so when you modulus it, it's the same as x plus 2 squared. Okay, so it really is the case that the modulus of x plus 2 all squared is the same as the modulus of x plus 2 all squared. So and I'll just subtract the half. Again, so we've simplified the question a little bit to this green form. Can anyone put any suggestions in the chat about what sort of branch of maths, what sort of thing, what sort of object this green, what can you say about x plus 2 squared take away 2 modulus x plus 2 plus a half? What type of object is it? Excellent, it's a quadratic. Okay, so we have a quadratic. So if I call x plus 2 modulus equal to just some new variable u, I've got that this is the same as u squared take away 2u plus 1. 1/2 is less than 0, which is the same as 2u squared take away 4u plus 1 is less than 0. And then I can solve this quadratic. I don't seem to be able to solve it nicely, but u is 4 plus or minus the square root of 16 take away 4 times 2, so take away the square root of 8 over 4, which is the same as 2 plus or minus root 2 over 2. And because it's a positive quadratic, so this is y equals 2u squared minus 4u plus 1, we have that 2 take away root 2 over 2 is less than u is less than 2 plus root 2 over 2. Okay, so what do we know about the modulus of x plus 2? We know that it lies in this range. But what's the lower bound for the modulus of x plus 2? Well, the modulus of x plus 2 has always got to be greater than or equal to 0. Okay, so we've now reduced to this inequality. Okay, because it's got to lie within this larger interval, but the modulus is always going to be 0 or more. What might be a good thing to sort of sketch or look at this point in order to understand the modulus function? Well, modulus inequalities, you probably know, are often best solved by sketching. So if I consider the graph y equals x plus 2, that can go negative, but then the modulus function picks it up and becomes positive. Now, what we want is we're looking for y values to be between 0 and 2 plus root 2 over 2. So we're looking for these. I might have done that a little. Oh, sorry. Someone saved me from a. Sorry, someone has saved me from a mistake. Yes, this 2 take away root 2 over 2 is actually positive. This is why it's nice to have a participatory audience. Of course, I just threw that little mistake. I just threw that little mistake in just to check that everyone, you know, was still listening. So this modulus function y equals x plus 2, the output needs to be less than 2 plus root 2. And now it's a strict inequality, but needs to be greater than 2 minus root 2 over 2. So we've got 2 extra points, which I'll call C and D. Okay, suggestions now for how I can find A, B, C, and D. So what I'll just to clarify what I want you to do in the chat, for part A, to find point A, can people put into the chat the equation that you would need to solve in order to find the x coordinate of point A? So think about how I got the graph of the function y equals x, modulus y equals x plus 2. I drew the line, and then when the line became negative, I flipped. Now the point A will be on that flipped branch. So for point A, I want the flipped branch, which is negative x take away 2, to equal the upper limit, which is 2 plus root 2 over 2. Okay, so now if I add 2 to both sides, I get something like negative x is equal to 6 plus root 2 over 2. So x is negative 6 plus root 2 over 2. Okay, and now I can find the other points. I can find point B. Actually, I'll do point C, which is again where the flipped branch is now equal to the smaller of the 2 roots. So I get negative x is 6 minus root 2 over 2. So x is negative 6 plus root 2 over 2. And now what range do I want for the modulus function to be sandwiched between the smaller and the larger number? I want the x values between A and C. So I want x to be in the range negative 6 plus root 2 over 2 is less than x, is less than negative 6 sorry, if I make a global minus here, that needs to be minus there. So -6 minus √2 over 2. Okay, and then I need to do something similar to find point B. So point B, I would have the unflipped line equal to 2 plus √2 over 2, which would give me x equals, if I subtract for -2 plus √2 over 2. And then D, I would have the same point but negative, and so I get a similar range, which is -2 take away √2 over 2 is less than x, is take away negative √2 plus √2 over 2. And then I get the union of those two intervals. Okay, so what were the morals of that question? Okay, this early part is the advantage, points to the need to sort of think at the start of the question, to spot a way to simplify. Okay, this, once we'd simplified to this, restricting the modulus to lying within a certain range, we see yet again the advantage of modulus inequalities of sketching things. Okay, so and the sketch really then helps us to identify the algebra that we need to do to find the 4 points. Okay, does anyone have any questions about that question that they would like to put into the chat? Are people happy with that question? Do people trust me? Do people agree with the result? Put a thumbs up if you're ready for me to move on to the next question. Okay, lots and lots of thumbs up. I promise I will, this PDF's become a little bit messy, so I promise I'll send these questions and write up the solutions a little bit nicer afterwards. Okay. I might come back to this modulus inequality a bit later, because I want to get on to some of the later questions, and I've got quite a hard stop at 7:30. So let's look at a logarithm inequality. So log 2x plus 2, it says, is greater than log 4 x squared. So my first question is, why is this question hard? And what would be natural to do to try and make it easier? Yeah, we could change the base. Okay. In particular, it would make sense to change the base to be the same thing. Okay, so what base would be a natural base to make everything equal to in the context of this question? Base 2, I agree. Okay, so what we've got is we've got log 2 of x plus 1 is greater than log 4 of, sorry, log 2 of x squared divided by log 2 of 4 to change base to base 4 And then we've got log 2 of x plus 1 is bigger than log 2 of x squared divided by 2. And what would be very sensible to do at this point, having learnt our lesson from earlier on when we did the square root functions. With the square root functions, by the way, I deliberately didn't think about restricting the range at the start because I really did want to get the wrong intervals. But here, I want to make sure that I restrict to x is bigger than -1. Okay. 2 is just a number. It's a nice positive number. I can multiply both sides of the inequality by 2. So I've got 2 log 2 x plus 1 squared is bigger than log 2 of x squared. Oops, sorry, I'm getting ahead of myself. And laws of logarithms, I can pass the 2 inside as a power, and I don't need to worry about anything because I'm restricting to x is bigger than 1. So I've got log 2 of x plus 1 squared is bigger than log 2 of x squared. Okay, and everything I've done so far is an if and only if statement. Now, what's very tempting to do here is just to get rid of the log 2's, okay, and to say that this means the same as x plus 1 squared is bigger than x squared. Is that step valid? And I imagine most of you will say yes, because it is valid. But then the most important question I'm going to ask now is, why is that valid? Why can I get rid of the sort of log 2? What justifies this? What justifies this step? Because it's a strictly increasing function. Excellent. Okay. And when you get towards sort of written papers and step quest papers or long math papers or things which require long written answers, you need to answer the question why. So the thing you would write here is because y equals log 2 of u is a strictly increasing function. Okay, so now we've got x squared plus 2x plus 1 is bigger than x squared. The x squareds go away. So we get 2x is bigger than -1. So x is bigger than -1/2. Does anybody have any questions about that example? If not, put a thumbs up. Good, lots of thumbs up. And the moral here is, you know, for step, write justifications like this. Okay. So I'm going to leave this this logarithm example is quite hard, and I'll come back to it later. Because I do want to talk about this question. And I just want to give a sort of flavor of, in these following questions, of inequalities in the kind of context that they often come up in. So it says in the diagram, so we've got a diagram here, and it says by considering various areas in the above diagram, show that for 0 is less than x is less than pi over 2, that x cos x is less than sine x is less than x. So let's consider some shapes. Now, there's some shapes that are all, in some sense, quite similar to one another. Okay, there's this triangle OAC, and that is clearly smaller than the sector of the circle OAC, and that in turn is clearly smaller than the right-angled triangle OAB. Okay, the radius of the circle is 1. So put it into the chat. I will do one area at a time. What's the area of the triangle OAC? So formula for the area of a triangle is half base times height. This height is the opposite of this right-angled triangle. So it's opposite over hypotenuse is sine. So this height is sine x. So half base times height would be half 1 times sine x. So it would just be half sine x. Alternative, you could have just used the 2 sides and the enclosed angle. I'm just checking the chat here that we've got sine x over 2 from lots of people. Okay, what about the area of the circular sector OAC? Notice the pi over 2 means that we should use radians. So if you want to put down the area of OAC in the chat, put it into the chat. Someone's put x. Let's be a little bit careful, because what fraction of, if you imagine the whole pizza, we've got x radians out of 2 pi radians. And then the area of the whole pizza would be pi r squared, and the radius is 1. So it would just be pi times 1 squared. So the whole area is pi. So the area of OAC is x over 2. And finally, what's the area of the right-angled triangle OAB? So it's a right-angled triangle, so we need to find the height, AB, and put some suggestions into the chat. So if we consider OA is the adjacent, if we sort of consider the right-angled triangle OAB, OA is the adjacent, AB is the opposite, so opposite over adjacent is tan x, so AB is tan x. Okay, so let's simplify these inequalities. We have half sine x is less than x over 2, which simplifies to sine x over x is less than 1. And then we've got x is less than tan x, and tan x is sine x over cos x. And then if we multiply both sides by cos x and divide by x, we get cos x is less than sine x over x. Actually, I've rearranged them into a slightly different form. If I multiply 3 by x, I get this inequality. Okay. And it was really that inequality that I wanted to show. But then part II, so it says, sketch on the axis provided on the opposite page the graph of y equals sine 1 over x. Now, again, we've got inequalities in mind. We know that sine is sandwiched between 1 and -1. So this function y equals sine x over x will always be sandwiched somewhere in the range between y equals 1 over x and y equals -1 over x. But what we also know is we know that it's bounded above by 1. So we know that this line y equals 1 is always above the curve. But what curve is sine x over x always above? If we look at this inequality, sine x over x always lies above the graph of cos x. So if I draw the graph of cos x, notice that that starts at 1 and then is 0 at pi over 2 and so forth. The curve that I'm sketching is always sandwiched between the purple line and the yellow line. And then it's 0 when sine is 0, so it's 0 at pi, and then 2 pi, and then 3 pi, and then 4 pi, and so forth. Okay, and then the points where it touches the line y equals x, or y equals 1 over x, is when the sine function is 1 or -1. In the context of the math question, it says justify the value that y takes as x becomes small. Well, as x becomes small, what would you say the value of sine x is, sine x over x becomes? So as x becomes small, what can you say that sine x over x is approximately equal to? 1. And notice this thing that it's asking you to do here is to justify. So how can we justify that the curve is becoming close to 1? Now, why? So sine x over x is close to 1 because it's less than 1, but bigger than cos x. Okay, because sine x over x is between cos x and 1, and cos x goes to 1. Okay. And Vlad's got his camera off. But, you know, anyone who's done maths, physics at university will be smiling at this point, because this is such a pivotal, such an idea that comes up so many times, that we've got some nasty function sine x over x that we don't particularly understand. But what we have done is we found inequalities above and below. Okay, so we know a little corridor that this function lives in. Okay, now the most problematic point of all of sine x over x is the point when x equals 0, because the top is 0, the bottom is 0, so it's all kind of undefined. But what we've got here is this pleasant situation where the corridor that it's in, so this corridor between the purple curve, which is cos x, and the yellow curve, which is y equals 1, becomes narrower and narrower and narrower and squeezes towards 1. Okay, and that's, you know, and that allows us to then give meaning and give value to the function sine x over x when x equals 1. And you will see this idea time, and this is a little sneak peek into the future. It's what physicists do all the time. They've got something really, really complicated. They make some assumptions and they find what's called an upper bound. Then they make some other assumptions and they find what's called a lower bound. And then if you really want to properly understand what's going on, you want to squeeze the upper bound and the lower bound together. And that's what happened. That's what has happened within this question. Okay, so I put this question in because it's on a mat. It's a nice example of inequalities, so it's not necessarily the sort of calculation of solving inequalities, but I just thought you would quite like to see kind of inequalities in action. Okay, I won't do the rest of the map problem unless people ask. There's a question in the chat. It's Vlad to say that he is smiling, and it really is. You know, you'll find that lots of people's research in physics is taking an upper bound that previous physicists have worked with and just make it that little bit smaller so it becomes a better upper bound, or to take a lower bound and to make it a little bit bigger and just get tighter estimates. Okay, any questions about that map problem, or put thumbs up if you're happy for me to move on. Okay, lots of thumbs up, which is good. Brilliant. Okay, so a little bit of background of this question. So I wrote the original draft of the inequality sheet, the sheet that you're working on. I put this question on, but it didn't quite make the final cut. But again, I just wanted to show it to you because it's an example of inequalities in action. Now I can hear a little bit of crushing and banging downstairs. Now I said at the start that my daughter was home alone. So I'm just going to give you a couple of minutes to read this question because I think it takes a little bit of processing. I'll just check what the crushing and banging is downstairs, and then I'll come back and work through it. Is everything okay? Well, I can't do that now because I'm still teaching, but I will make it. Okay, so the following figure shows the graph y equals e to the x, along with a tangent drawn at the point x equals 0. So first question, find the equation of the tangent. Does anyone want to put a suggestion for the equation of the tangent into the chat? Y equals x plus 1. Excellent. Okay, part B. Explain why the curve y equals e to the x always lies above the tangent line. Does anyone want to put into the chat a sort of verbal explanation? What in particular, is there a property of the curve y equals e to the x which kind of guarantees that the curve is above the line? Okay, so someone has said e to the negative powers is still positive. Okay, but that only deals, so if x is bigger than -1, that's enough. Because if x is bigger than -1, we know that y equals e to the x is positive and the line is negative. But it might be that the curve is below the line in this section here between -1 and 0. There's a property of the curve y equals e to the x which guarantees it lying above its tangent. Well, someone suggested strictly increasing, but that's not enough, okay? Because here's a curve that is strictly increasing. Okay, y equals x cubed. But if I draw a tangent line here, the tangent is initially below the curve, but crosses the curve and goes beneath it. So it's not enough to say that y equals e to the x is strictly increasing. That's not enough to guarantee that it lies above its tangent. Think cycling. Okay, so let's start at this point, 0, 1. Describe the experience of cycling along the up the hill y equals x plus 1. So cycling along the line y equals x plus 1 is just going up a constant gradient of 1. But what happens when you cycle along the curve y equals e to the x? What happens to the gradient of the curve? It gets steeper. Okay, so here for x is greater than 0, okay, y dash is always bigger than 1. So the curve y equals e to the x is steeper than the line, and that means that it goes above it. Which is steeper to the left of the point x equals 0, 1? So which is steeper if x is negative? Well, again, because the y equals e to the x curve is always getting steeper, because its gradient is just the e to the x, which is an increasing function, y equals e to the x is always getting steeper. So it's for negative values of x, y dash is less than 1. So the curve is less steep. Okay, so if the curve is less steep than the line is going down quicker. On this side, if the curve is more steep than the line, the curve is going up faster. Okay, so the curve, what property was it that guaranteed that the curve lay above its tangent? Well, y equals e to the x lies above its tangent line. Okay, this holds because the gradient of y equals e to the x is increasing. Now, in the chat, and this goes back to this topic of the last webinar, can anyone give me a shorter way of writing that statement? So I've written quite a long-winded statement there that says this holds because the gradient of y equals e to the x is increasing. Can anyone give me a simpler, shorter way of writing that same fact? No points of inflection and the derivative is always positive. Not quite, actually. Okay, because here's a function with, that's what someone suggested in the chat, no points of inflection and the gradient is always positive. Well, here's a function which has got no points of inflection and the gradient is always positive, but it's certainly not the case that the gradient is increasing. Excellent. Someone's actually jumped, well, no, someone's put the right thing. So the gradient is increasing. Now a function is increasing if its derivative is positive. So we want the derivative of the gradient to be positive, but the gradient is the derivative. So we want the derivative of the derivative to be positive. So the reason the tangent always lies above the line is because the second derivative is positive. Now, can anyone do even more concise? Can anyone express that concept in a single word? There's a single word that just means y to the double dash is bigger than 0. Convex. Excellent. Okay, so we've got this nice property that a convex curve always lies above its tangent. Now, this red function that I've drawn here is y equals ln x. What can you tell me about ln x related to its tangent? So if I draw a tangent to y equals ln x, where will that tangent be? The tangent will always be above log x. Okay, that follows because that's just the mirror image of the tangent to y equals e to the x. And what's the shape of y equals log x? Well, it's a curve which is getting less steep, so it is what's called concave. So we've got this nice little relationship that if y double dash is bigger than 0, and that's when the curve is convex, then the curve is above the tangent. And a curve is concave if y dash is less than 0, and in that case, the tangent is above the curve. Okay, next part. Prove the inequality e to the 1 over n is bigger than 1 plus 1 over n. Well, we've just seen that the curve is above the tangent, so we know that e to the x is always bigger than 1 plus x. So if I just put x equals 1 over n, I get e to the 1 over n is bigger than 1 plus 1 over n. So that was nice and easy. And if I just raise both powers, if I just do raise both sides to the power n, I now get that e is bigger than 1 plus 1 over n to the n. So if I look at my part D, I've done this part. Okay. Any suggestions of any hunches, any ideas of what I might want to look at to get what point I might want to give you a clue that I'm going to start using this inequality that e to the x is bigger than 1 over x. What point do you think I might want to use to get the green inequality? This is a good intuition test. Stare at the terms, stare at the powers. Remember, you're going to need to get something to get the inequality the other way around. It's a very tough question. I'm not surprised there's not many answers in the chat. And in some ways, I think if you're watching this on, catch up, I would pause the video here and I would really try and think about this right-hand side, and you'd probably try lots of different cases. I'll give you a little bit of intuition of how to think about it. Well, firstly, I can see that I've got this power of n plus 1. So 1 over n plus 1 makes sense. But I want the e function, I want the inequality to be the other way around. So doing a negative number seems like a good thing to try. So what I'm going to use is I'm going to use x equals negative 1 over n plus 1. So I get e to the negative 1 over n plus 1 is bigger than 1 minus 1 over n plus 1. If I simplify the right-hand side, that right-hand side becomes n over n plus 1, and the left-hand side is 1 over e to the 1 over n plus 1. I don't like the fractions, so if I multiply both sides by e to the 1 over n plus 1, and then n plus 1 over n, so if I just multiply by n plus 1 over n times e to the 1 over n plus 1, which I can do, which is because it's positive, I get n plus 1 over n is bigger than e to the 1 over n plus 1. And now if I raise both sides to the power n plus 1, which I can do because y equals x to the n plus 1 is a strictly increasing function, so e is less than, and n plus 1 over n is 1 plus 1 over n to the n plus 1. So I get this, I get 1 plus 1 over n to the n is less than e is less than 1 over n to the n plus 1. Okay, why is this? Can anyone give me a suggestion of why this inequality is useful? What does this inequality give me a way of doing? It gives me a way of approximating e. Okay, so if I put n equals 1000, okay, you can get a calculator and you can do 1 over 1000 and raise it to the power 1000. Actually, if I go to a different screen, I'm just going to stop my share and I'm just going to share a different screen. Okay, and I'm just going to do that. I'm going to do 1 over 1 to the power 1000, and I'm going to raise it to the power 1000. Sorry, this machine is a bit too powerful, so that's given it to me as a fraction. But if I do it as a decimal, let's just do a few more decimal places. So I'll do it to 1000 decimal. Oops. I'll do 100 digits. Okay, so that's not 100 digits, but never mind. Oh. Okay, that's a lot of digits. Anyway, you can see that this is a good approximation to E. If I put a few more, if I take a higher power, I get an even better approximation to E. Okay, so this is really good, is that it gives me an approximation for E. But why is the inequality? I could have just written E is approximately 1 plus 1 over n to the n. Why is this green inequality better? What extra information is contained by the green inequality? If I go back to my other window, this is the left-hand function, so the 1 plus 1 over n to the power n, and this gives me an approximation to E. I also get an approximation to E if I raise it to the power of n plus 1. But the thing which is really powerful is that I know E lives between these two numbers. Okay, so it doesn't just give me a approximation, it gives me a range. And obviously, because the range is just an extra factor of 1 plus 1 over n, okay, I know that the percentage, I can calculate the sort of percentage error, and I know that the percentage error is small. Okay, so what this guarantees, is, well, I could, if I divide through by e to the 1 plus 1 over n, I get a similar picture to the last question, where I get that this term is this time above 1, but then it's below 1 plus 1 over n. Now, what happens to 1 plus 1 over n? As n becomes big, that becomes closer and closer to 1. So what I can see is that this fraction is sandwiched in this range. So just like the sine x over x, I know that the limit of, as n goes to infinity, of 1 plus 1 over n to the n is E. And that's a really, really nice result. Okay. Final thing. Hence prove these inequalities. I'll just do one of them. What do you think the natural thing to do if we want to get an inequality? We've got an inequality about e to the 1 over n, and I want to get some inequality, involving 1 plus a half plus a third plus 1 over n. What would be a natural thing to look at? So I want to get an inequality involving 1 plus a half plus a third plus 1 over n. And I know that e to the 1 over n is bigger than 1 plus 1 over n. And that's n plus 1 over n. If I want to understand this term, and I've got this inequality, a natural thing to look at would be to look at e to the 1 plus, and then, so e raised to the power of that sum. Now, if you do e to the sum, what is e to the sum the same as? Oops. So people are saying they can't see the share. So I'm not sure where people lost me, but I'm doing this part E. So I'm trying to get an estimate for 1 plus a half plus a third plus ... 1 over n. And my starting point is this inequality, that e to the 1 over n is bigger than 1 plus 1 over n. Okay, so this is what I'm trying to estimate. And this is my starting point. Now, what I'm looking at is I'm now looking at e raised to the power of 1 plus a half plus a third plus ... 1 over n. Now, e to the sum is the same as what? So if you do e of a plus, what is e of a plus b? The same as? Well, e of a plus b is the same as e of a times e of b. Sorry, can people just put a thumbs up if I'm back on the right screen and everyone's happy? Yeah, good. Okay, so e to this sum is the same as e to a product. So I've got e to the 1, e to the half, e to the third, e to the 1 over n. But I've just got, in this box, I've just got a nice set of inequalities that I know that e to the 1 over n is bigger than something. So for example, I know e to the 1 is bigger than 1 plus 1 over 1, which is the same as 2. Okay, that's not a particularly good approximation, but we know that E is bigger than 2. When I use this inequality star for E to the half, what can I say that E to the half is bigger than? So what do I get if I put n equals 2 into this inequality? So I've got e to the 1 over n is bigger than n plus 1 over n. What happens when n equals 2? So when n equals 2, this fraction is 2 plus 1 over 2, which is 3 over 2. When n is 3, e to the 1 over 3 is bigger than 3 plus 1 over 3, which is 4 over 3. All the way up to e to the 1 over n, which is bigger than n plus 1 over n. That's just my inequality star. What nice thing happens to this product? So I've got 2 times 3 over 2 times 4 over 3 times ... n plus 1 over n. People should be happy at this point. What happens to this 2 and this 2? Well, they cancel. This 3 and this 3 cancel. In fact, everything cancels apart from the final n plus 1. Okay, so I get this nice result that 1 plus a half plus ... 1 over n is big. Sorry, e to that is bigger than n plus 1. And then when I take logs, I get that 1 plus a half plus 1 over n is bigger than log n plus 1. Okay, and I'll leave it as an exercise. But how do you think you'll get the other inequality? Well, the other inequality will follow from the green inequality here, the e to the 1 over n. Yeah, the other inequality, and I'll leave that as an exercise. Okay, and so what we've kind of shown is that this, and again, you will meet this again in the future. With less care, I could have just written an approximation that 1 plus a half plus 1 plus 1 over n is approximately the natural log of n. But what I've got here is yet again some complicated term in the middle, and then an upper bound and a lower bound. Okay, and that's, you know, that's the sort of riff of that last part. Okay, now I hope you've enjoyed these last 3 questions. As I say, they are a window of the world of something that you do a lot in maths and physics, of using inequalities to find upper and lower bounds. So I hope those last 3 questions were interesting. Okay, the earlier questions covered questions that were a little bit like the ones on the sheet. And the moral was for the ones involving logs and the ones involving moduluses and square roots, is that the algebraic processing was no harder than what you did last week with the rational inequalities, but needed to be very careful about signs, S-I-G-N-S. Okay, so that's what I wanted to say. Does anyone have any final questions before I finish? Okay, well, I hope people have enjoyed the webinar. I will write it all up. Vlad, I'll put the questions together into my PDFs, a little bit scrappy, but I'll write it up nicely and send it to you.
Oh, lovely.
And I hope people enjoyed it.
All right, thank you very much, David.
Yeah, lots of thank yous in the chat. So enjoy the rest of your evening. Okay, I'm going to leave. Bye bye, everybody.
Okay, bye. Thank you.